All right. So I'm going to imagine I just walked around the classroom and I see most of you guys are done. So let's go over this warm up. All right. So like I said, these are both Regents multiple choice questions. These are usually on the harder end. Well, let's take a look. So this first one, last year, the total revenue from for Homestyle, a national restaurant chain, increased 5.25% over the previous year. If this trend is going to continue, what can we use to approximate their monthly percent increase in revenue? So we know it's a 5.25% increase, right? And that is in a month. Sorry, in a year. So what can we do to find a percent increase in a month? Oh, why don't you guys type your answers in chat? What do you guys think you can use to get the monthly? Type in 1, 2, 3, or 4. 3 question mark. All right. I saw 3 question mark and then a bunch of 3s. So it seems like you guys are getting the right answer. Maybe some people aren't too sure why it's 3, but yes, the correct answer is 3. So let's take a look at this. So if it's a 5.25% increase in a year, I'm just going to do this diagram thing again. 1, 2, 3, 4, 5, 6. Let's say there's 12 spaces there, right? In 1 year, we're going to be multiplying by 1.0525, right? If that's a 5.25% increase, right? And that's in a year. So if you want to get the growth factor for each month, well, if there's 12 steps, I'm going to have to multiply by 1.0525, right, to the 1/12th power. So our monthly growth factor is 1.00427, right? That's the 12th root of 1.0525. And if that's our monthly growth factor, that means each month we're growing by 0.427%. And so that's our monthly growth factor. That's just to the m power for each month. And that's choice 3. All right, good? All right. Second one, you have the decade growth rate, and you want to get the yearly growth rate. So it's just like the previous problem, right? If our decade growth rate, actually not growth rate, our decay rate is 25%, right? We're multiplying by 0.75 over 10 years. So each year, that's going to be 1/10 of that, right? 10 years in a decade, and that's approximately 0.9716. So each year, that's also going to be choice 3. All right, cool. Any questions? No. All right. So the trickier part is this part down here. Write an equation using the yearly decay factor in terms of decades D. All right. So when we had the equation for choice 3 here, right? That was a function in terms of the year. I'll call it P of y. That equals 714 times 0.9716 to the y power. But I want to use that same yearly growth factor, 0.9716, but instead, I want this to be in terms of D here, right, in terms of the decade. So what a lot of people are going to do is they're going to say, all right, 10 years is equal to 1 decade. So they're going to think, all right, if I want it in terms of D, a decade is 1/10 of a year. And they're going to write D over 10 here as the exponent. But actually, it's going to be to a power of 10D. So let's see if this makes sense. If you're using the yearly, growth rate and we want to have a time in decades, well, we know 10 years is equal to 1 decade, but that does not mean 10y equals 1d. I'm going to use the letter D for decade. Because if you think about it, let's say we have 1 decade, so D is 1. So we're going to be saying that 1 decade is equal to, well, we know a decade is 100 years, that's going to be 100. That doesn't make any sense. So this is not true. What we should be saying is that 1 year, or 1y equals 10d, right? I know that seems weird, it seems counterintuitive, but if 10 years is equal to a decade, then we can say 1y equals 10d, right? And if you plug in numbers, it should make sense. For example, if d is equal to 1 decade, then y is equal to 10, right? If d equals 1, then y equals 10. That's 10 years. Does that make sense? If d is equal to 2 decades, then y is going to equal 10 times 2, or 20 years. Yes, this is the most confusing part of this lesson and the last lesson. But if 10 years is equal to 1 decade, then we can say y is equal to 10d. Right, d is the number of decades, y is the number of years. So 1 decade, if d equals 1, then y equals 10. Would you guys agree this is true? 1 decade is 10 years.
Yeah, I get it.
So does it make more sense, Grace?
Can you clarify why this reversal works?
All right, kinda, I'll take kinda for now, right? If d equals 2, then y equals 20, right? 2 decades is 20 years. So that's gonna be that, and there we go. That's the equation using the yearly decay factor, right? Yearly decay factor was 0.9716, right? And then instead of y, we just replaced it with 10d. So now it's in terms of decades rather than in terms of years. All right, cool. So yeah, just the trickiest thing, a lot of people are gonna write d over 10 rather than 10d, right? So the y and the d here, right? Over here, these are units, right? 10 years is equal to 1 decade. But when you write it as an equation, it actually becomes y equals 10d, not 10y equals 1d. Right? You can't just make units into variables, and that's the mistake most people make. All right, so moving on. I like this problem over here. We got Pedro and Bobby, they own ant farms. Pedro has 1,000 ants, and his farm is growing exponentially at a rate of 15% per month. All right, so we can write an expression or an equation for Pedro's ants. I'm going to use the letter T for Pedro. So Pedro's ants, as a function of time, right, they're growing by, well, he starts with 1,000. It's growing by 15%. So that means the growth factor is 1.15. Can you guys hear my kids in the back?
Yeah.
Okay, I'm gonna tell them, hold on. All right, door's already closed. All right, I'm sorry. So P of T equals 1,000 times 1.15 to the T power. Right, Bobby, well, he has 3,500 ants. So B of T, so this equation represents Bobby's ants. B of T is 3,500, and it's decreasing by 2% per day. So that will be times 0.98 to the T power. And when are they going to have the same number of ants after how many days? So guys, there's a problem with the way I set up my two equations. Does anyone see something I did wrong?
One of them is per day and one of them is per month.
Exactly, yes. So I can't use the same variable T, so I gotta switch it up. So for Pedro, it's per month, so I'll use the letter M for months here. right? And for Bobby, it's in days. So I'll use the letter D for days. And the question is asking, after how many days will they have the same number of ants? So again, I have to do a unit conversion here. So if I want the answer in days, well, I'm going to change Pedro's equation into in terms of days. Right? So we know his monthly increase is 15%. Let's try to write it in terms of a daily increase. So let's change this to the number of ants as a function of days for Pedro. So if it's a 15% increase over a month, and we're assuming there's 30 days in a month, well, his daily rate of increase then is going to be 1.15 to the 1/30th power, right? 30 days in a month. So each day, it's going to be the 30th root of the monthly growth factor. Does that make sense? All right, if you don't say you're confused, I'm going to just keep going. So you can get that as a decimal if you want, get a decimal approximation for the daily growth factor. But we can also just leave it like this for the exact value, right? 1.15 to the 1/30th. This entire thing right there, right, that was our daily growth factor. Right, so if it's daily growth factor, then that's to the D power, right, for any number of days. So we know when we have a power to a power, we can multiply. So I can write this as 1.15 to the D over 30th power. All right, so let's see if this makes sense. In 30 days, right, I'm going to grow by 15% because 30 days is equal to a month. So I can replace that D with a 30, and it's 30 over 30. Right, so in 30 days, we grow by 15%. Right, in 60 days, or 2 months, we're going to grow by 15% 2 times. So really what we just did is we just did a unit conversion again. Right, we know 30 days is equal to 1 month. So the equation that follows from this is not 30D equals 1M. Right? Just like before with the decades and years, this is actually the trickiest part. What we can say is that 30M is equal to D. And again, if that doesn't make sense, pretend M is equal to 1. Right? If M is equal to 1, 30 times 1 is 30 days. D equals 30. Right, so that's the equation we're actually using. And if you look solving for M here in this equation, right, M equals D over 30. So that's really what we did to go from this to this. And now it's in terms of days. All right, questions? All right, so approximately how many days will they have the same number of ants? Well, we're just going to set our 2 functions equal to each other now. So we do not know how to solve this yet algebraically, but we can do this on Desmos or on your graphing calculator. So you're going to graph this function, and you're going to graph the other function, and we do that to see when they are equal to each other. All right, so if I switch over to Desmos, one of them was 1,000 times 1.15 to the, what was it? What was the exponent? All right, it was D over 30. All right, to the X over 30th power. Right, and other guy was 3,500 times 0.98. It was decreasing by 2% each time. And that was just to the X power, right, where X was number of days. Let's scale our axes a little bit. bam, there are two functions, right? One's exponential growth, one's exponential decay. And we can see they intersect at approximately 50.39. So after 50-ish days, right, both ant farms will have about 1,264 ants. So after approximately 50 days. All right, how is that?
Good.
Good, all right. So today's lesson, it's a quick one. We're talking about half-life. All right, so really today's lesson is just introducing vocabulary word, which is half-life. Oh no, oh no, okay. So the half-life of a substance is the time it takes for a quantity to reduce to half of its initial value. And that's it, that's the definition of half-life. So a radioactive iodine has a half-life of 60 days. This means that half of the substance remains after 60 days. So what is the daily rate of decay to the nearest hundredth of a percent? So we know the 60-day rate of decay. We're looking for the daily rate of decay, right? So in 60 days, we lose 50%. In other words, we can say it's a 50% decrease, right, in 60 days. So if you want the percent decrease in 1 day, well, it's going to be just like how we've done all the other ones, right? It's going to be 0.5. Well, I actually can't do that yet, but the way we'd find it is the decay factor is a half or 0.5. If it takes 60 days to decrease by 50%, in 1 day, it's going to decrease by 1/60th of that amount as an exponent, right? And that is approximately 0.98851 something, something, something. And so that is our daily decay factor, right? We're going to multiply by a half for 60 days. And in 1 day, we're going to multiply by this amount each time. And that's our daily decay factor. So our daily decay rate, is 1 minus r. That's going to equal that number, 0.988514. And solving for r here, we get 0.01148 something, something, something. 979. So it asks for the nearest hundredth of a percent. Make sure you're not rounding this decimal to the nearest hundredth. You want the percent to the nearest hundredth. So changing this to a percentage, remove the decimal 2 places to the right. That's 1.148 or 1.15 if we round. So the daily decay rate is 1.15%, right? We're losing 50% in 60 years. Each day, we lose 1.15%. All right, questions on that first part? All right. So if the initial amount of the substance is 80 grams, write an equation for this function which models the decay of a sample of radioactive iodine where I grams of the radioactive element remain after T days. So the amount of iodine is going to equal the initial amount, which is 80. And I'm going to use my daily growth factor. Not growth, sorry, daily decay factor, which was 0.988514 ... right, to the T power. So sure, I could write it like this, but this is actually not the best way to write this because I'm using a decimal approximation inside that parentheses there, right? So even though this would be okay for doing calculations, the way I want you guys to write it is, instead of using the approximation, why don't we just use the exact value? We know if the half-life is 60 days, then the exact daily decay factor is going to be 0.5 to the 1/60th power, right? The 60th root. So we can also write this like I of t equals 80 times 0.5 to the 1/60, right? That's this guy. And that's going to be to the t power. So if I multiply, sorry, if I raise this to the t power, I know I can multiply the exponents. So can I simply just say 0.5 to the t/60? All right, cool. Right, these two are equivalent. But this is nicer. First of all, the equation's a lot simpler. You don't have so many decimals, and just a lot cleaner. All right. And once we have this, how much of the original sample will be present in 180 days? Well, we can plug in I of 180 equals 80 times 0.5 to the 180/60. And then 180/60 is 3. So that's just 80 to the 0.5 to the third power. And that's equal to, all right, if we're having 80 3 times, it goes 80, 40, 20, 10. That's 10. So we're going to have 10 grams left over after 180 days. Right? If we think about the definition of half-life, this should make a lot of sense. Half-life is the amount of times it takes to decay to half the original amount. So if the half-life is 60 days, well, in 180 days, won't it decay in half 3 times? Right? 180 divided by 60 is 3. So we start with 80. After 60 days, we're going to have 40. After another 60 days, we're going to have 20. And then after another 60 days, we're going to have 10 grams, right? Which matches exactly how we wrote our equation. And then for something like letter D, which asks in approximately how many months to the nearest tenth, will we have 15 grams present? So we're going to make I of t our final amount, 15 equal to 80 times 0.5. And now we're solving for the exponent. We're solving for t in this case. And to solve something like this, again, just type it into your calculator. Graph y equals 15, graph that function, and see where they intersect. All right, cool? So I'm going to graph that real quick. $80 times a half raised to the, what was the power again? t/60, x/60. And we're also graphing y equals 15. Go back home. And it's going to take 144.9 days. To the nearest tenth, so 144.9 days. Right, and this answer makes sense because if we compare it with our previous answer, we know in 180 days, we're going to be left with 10 grams. So when are we going to be left with 15 grams? Well, that's obviously going to be less days than 180. And so that seems about right. Yes, very cool. I don't know when you said that, Louis, but yes, this is good stuff. All right, number 2. Cobalt-60 has a half-life of 5.26 years. And these are all real numbers, by the way. Half-life is a real thing. We'll talk about how people actually use half-life in a second. But in approximately how many years will 10% of the original mass be present? Oh, they don't even give us an initial amount here. All they give us is a half-life of 5.26 years. So, what can we do here? Well, we know half-life is the amount or how long it takes for us to be left with half the amount of material. So we have a 50% decrease, right, in 5.26 years. So how can we get the decrease in 1 year? So this is a weird number, but based on everything we've been doing, it's always been the same to get the yearly rate of decay, right? And what we're going to do is we're going to take the 5.26 root of 50% or a half. Right? If we know it decreases by a half in 5.26 years, in 1 year, it's going to decrease by a half to the 5.26 power. Does that make sense? Right? If that doesn't make sense, imagine it was 10 years, right? Then it'll be a half to the 1/10, right? So same concept, it's just not a nice number this time, but we've been building up to this. So hopefully that's okay. So if we were to write our equation, well, A of t, the amount after t years, is going to equal the initial amount. Here is our yearly decay factor, right? All of this to the t power. So I can just say to the t over 5.26. All right. So after how many years will we have 10%? But we don't know the original amount, and we don't know the final amount, but we know 10% is left over. So let's just pretend we started with 100 grams initially. Right? If we start with 100 grams initially, what we're going to be left with is 10 grams at the end. Right? So I can say A of t is 10, and the initial amount is 100. And that's a half to the t over 5.26. So dividing 10 by 100, I get 0.1 is equal to 1/2 to the t over 5.26. So it actually doesn't matter what the initial amount is, because if I started with 200 grams, for example, right? If I'm left with 10%, I know A of t, my final amount will be 20. If I started with 300, my final amount will be 30, etc. Right? So we don't even need to know the initial and final amount. It's always going to be equal to 0.1, and that's 10% after the end. Right? So we can say this ratio of the final amount, A of t, over the original amount, right? That's always going to be 0.1. But if you don't like that, just make up a number. Just make up, okay, we had 100 originally. We're going to be left with 10 grams at the end, and that's going to be 0.1. So again, to solve this, we're going to graph. And graphing this, we're going to get an answer of t is approximately, did I write this one down? I did not write this one down. I'm going to do it on my computer real quick. So y equals 0.1. And, well, I actually did do it. It's right there. So graphing both of those equations to the nearest hundredth of a year, that's going to be 17.47 years. You don't get this. All right. How you guys feel about this? Besides Eric. Raymond's okay. Anyone else confused? All right, so I'm gonna go a little bit more into it for Eric, but whatever this half-life, we're gonna come up with a general formula for it now. So again, half-life is how long it takes to decay in half. So it's giving us a 50% decrease in 5.26 years, which was the half-life. Right, so if the half-life were 10 years, like we said, right, then to get the yearly decay factor, it will be 1/2 to the t over 10, where t is number of years. So it's just a weird number here for the half-life, but it's the same as what we've been doing. And actually, however many years the half-life is, that's what's going to be over here in the denominator. So we don't really need a general formula for half-life, but if you want, we can say the final amount of a substance, A of t, is going to equal the original amount. And because we're talking about half-life, this guy in here is always going to be a half times a half. Right, so a half to the t power, and it's going to be divided by, well, when the half-life was 60 days, it was t over 60. When the half-life was 5.26 years, it was t over 5.26. If the half-life is 10 years, it's going to be t over 10. So in general, a half-life formula, if you want it, is just going to be t over h, where h is the half-life. So A of t, that's going to be the final amount, or the amount after t number of years, right? A sub O, that's our initial amount. And the only other thing we need here is the h. The h is going to be the half-life. And again, half-life, definition's right up there. Half-life is a measure of time, right? It's how long it takes for the substance to decay in half. All right, so here is a formula. I don't need to give you a formula, but there it is, right? We should be able to do this without needing the formula because it really is just changing our rate of decay from however many days or however many years to a standard unit of 1 day or 1 year or 1 month, etc. All right. So that's really it. I'm actually probably done with the lesson. At this point in class, I have some practice problems you guys can try. So stick around if you want to go over these. But if you feel like you got it, you can try these on your own and then check with the video lesson later. But if you want to go over a couple more problems, let's talk about it. So first of all, half-life, it's pretty cool. Half-life is a thing in real life people use. All right, so how is half-life information used in carbon dating? It lets us date the ages of very old things. So scientists can use the half-life of carbon-14. You might have heard of carbon-14 before. That's the most popular radioisotope they use for determining the age of something. So that can be used to determine the age of organic objects less than 40,000 years old by determining how much of the carbon-14 has transmutated or decayed. Scientists can calculate and estimate the age of a substance. This is called carbon dating. And you can use different isotopes to date other kinds of things. So examples, archaeologists use carbon-14 dating to determine when very old organisms died. All living organisms contain carbon, which is continuously replenished through food and air. Carbon-14 decays over time to carbon-12. When an organism dies, this decay continues, disrupting the normal ratio between carbon-14 and carbon-12. So by measuring how much carbon-14 and carbon-12 is in organic matter, they can figure out how old something is. So Dr. Jones has discovered a mummy which contains only 35% of its original carbon-14. Knowing the half-life of carbon-14 to be 5,730 years, how many years have passed since the death of this mummy? Round to the nearest 10th of a year. So it contains 35% of its original carbon. If you want, you can just say, if it's 35%, then that the ratio of the final amount, right, over the original amount has to be 0.35. If you don't like that, then just make up an original amount. You can say the mummy was 100 grams at the start, and then if only 35% is left over, then at the end, we're gonna have 35 grams. And you can plug those numbers into your equation, right? But once you do, what is it? 35 divided by 100, you're gonna get 0.35. So knowing the half-life of carbon-14 to be 5,730 years, well, it's gonna decay in half in 5,730 years. So how much is it going to decay by in 1 year? Well, in 1 year, it's gonna decay by a half to the 1 over 5,730th power. Right, 1 5,730th. You can think of 5,730 steps, right? We're taking one of those 5,730 steps per year. So that's a half to the that power. And that's it. And that's what we're solving. So again, to solve this, you need to graph. All right, graph to solve. Graph to find t. If you did not like the 0.35 and where that came from, again, you can just make up any initial quantity. Let's say 100 is nice. We discovered a 100-gram mummy. It has 35% left over at the end. So the final amount is 35. You do 35 divided by 100, and that's where this 0.35 is coming from. All right, cool. So just like the last one. And let's do one more. All right, titanium-44 is a radioactive isotope such that every 63 years, its mass decreases by a half. So it has a half-life of 63 years. So if you want, let's use the formula for this one. For a sample of titanium-44 with an initial mass of 100 grams, write a function that will give the mass of the sample remaining after any amount of time in years t. So the final amount after t number of years is going to equal our original amount, 100. We're talking about half-life. So it's going to half in 63 years, which means in 1 year, it's going to get multiplied by a half to the 1 over 63rd power. And if I copy and paste this formula, from over here, you can see how the parts fit in. All right, so all I did is plug in for the original amount, and I plugged in 63 for half-life. All right, using your function from part A, calculate the mass remaining after 40 years, round to the nearest 10th. So after 40 years, we're going to plug in the 40. So 100 to the 1/2 to the 40 over 63 power. Right? We can see that 40 years is less than 1 half-life. Right? So we're raising a half to a power that's less than 1 because it's not going to decay in half yet after 40 years. It's going to be a little less than half. So if we evaluate this, 100 times 0.5 to the 40 over 63. That is 64 point, nearest 10th, 64.4 grams. right? And again, 40 years, less than 1 half-life. So look, it did not decay in half yet. It decayed by less than a half, right? Half of 100 is 50. We're left with 64. So you can do a quick check to make sure your answer makes sense. If you're getting a number less than a half, well, that has to be more than 1 half-life. And this last one, just another one we're going to do on the calculator. How many years to the nearest tenth will it take for the original sample to decrease to 10 grams? So we make 10 equal to our equation, 1/2 to the t over 63. All right, I'll let you guys practice graphing this on your own. See where they intersect, and you get that value of t. And that is it. Thank you for joining me today, guys. If you have any questions on homework or anything else, you can stick around and let me know. But that is going to be it for Half-Life today. All right. So, you guys good? Any questions? You're very welcome, Nate. Thank you for coming. All right, I'm just gonna stick around for a couple more minutes in case you think of any questions. You can think of this as extra help. Go ahead, Raymond. But your notes aren't loading. All right, well, I'll stick around for a little bit more, probably till at least 2 o'clock. All right, so Raymond, question lesson number 4. Question 3. Bi-yearly, okay. How come you squared the result from yearly? Because if I have my yearly rate, so let me draw a picture for this. Actually, let me make a copy of these notes first. Duplicate, and I can edit that new version. All right. So if my yearly rate of growth is 1.005, I'm just going to approximate and say the yearly rate of growth is 1.005. All right, I'll keep the decimals, 1.005177. That means going from 1 year to the next, I'm going to multiply by 1.005177. So if I want the bi-yearly rate, bi-yearly just means in 2 years. That means I'm going to multiply by 1.005177 2 times, or 1.005177 squared every 2 years. All right, so that is my bi-yearly growth factor. And then solving for the bi-yearly rate, just subtract 1, get it as a percent, and that's that. All right, good? You could also just take the 20th root of the decade growth rate to get the, is it the 5th root, I'm sorry, the 5th root of the decade growth rate to get the bi-yearly growth rate, right? Because there are 2 sets or 5 sets of 2 years and 10 years. So that would also be the same thing. Oh, okay. I get it. Yeah, bi-yearly is not something that you see too often. I'm not even sure if that's correct. If bi-yearly means, all right, so what I meant by bi-yearly was 2 years. I don't know if that's correct. English or not, I'll double check on that. Sorry for that confusion. Do you guys like the Zoom calls? All right, I'll try to do it more often. I can't guarantee I have time available every day to do this, but yeah, I'll try to do it more often. I'll let you guys know when I will be doing one. And I'll just post up the video also as normal in case you can't make it, because I know when you guys are at home, you guys have things to take care of, schedules. So, growth factor and the rate. Sure. So, growth factor is what we're multiplying by, and rate is like the rate of growth. So let's say something is growing by, let's keep it simple, like by 10% a year, right? If something's growing by 10% a year, growing by 10% a year. Let's say you had a savings account. Whose mic is that? All right, thank you. All right, so let's say you're investing in a savings account that's growing by 10% each year, and you invested $100 into this account. All right, so to find the amount after 1 year, well, you could multiply by 1.1, right, after 1 year. So the 1.1, we call that the growth factor. Right, the word factor means something you multiply in a product, right? So 1.1 is the growth factor. All right, bye, Eric. See you. Thanks for coming. This 10%, that's the growth rate. So R equals 10%, and 1.1 is the growth factor. That's it. That's the difference. So in the formula for exponential growth, right, the amount after time t is going to equal the original amount times 1 plus r to the t power. So a growth rate of 10% means this r is 10. But a growth factor is going to be 1 plus the 10%, or 1.1, and together that's the growth factor. So it's really just vocab. That's the difference between the two. Did that make a little more sense? All right. Like after 2 years, you're going to multiply by 1.1 2 times. Right? After 3 years, it's 1.1 3 times. So in general, the formula after any number of years is A of t equals the initial amount times your growth factor to the t power. But the rate is just the percentage, right? And the growth factor is 1 plus that percentage. That's what we use to multiply in the equations. All right, good. No problem. The second to last question on the homework that was due yesterday. All right, what was the homework due yesterday? What was yesterday? Yesterday was Wednesday. Was it assignment 4 or 3 that was due yesterday? 4, I'm guessing. All right. Second to last question. This killer regions problem? Oh, assignment number 0333. All right, assignment, that's right. Second to last one. Oh, this grandfather clock one. Oh, I don't even know why I put this question on here. I didn't like this one too much, but large grandfather clock. Wait, second to last one. All right. This is the question you want, right, Grace? This one, question number 4? All right. So a large grandfather clock strikes its bell at 1 o'clock, 2 o'clock, and 3 o'clock. Right? At 1 o'clock, it strikes once, 2 o'clock 2 times, 3 o'clock 3 times. So at 12 o'clock a.m. and 12 o'clock p.m., it's going to strike 12 times. Right? At 11 p.m. and 11 a.m., it's going to strike 11 times, etc. So what is the total number of times the bell will strike in a complete day from 12 a.m. until 11 p.m.? So use an arithmetic series to help you solve the problem. So if I write out all the hours of the day, right, it's going to go 12 a.m., 1 a.m., 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 a.m. Then we're going to go 12 p.m., 1 p.m., 2 p.m., 3 p.m., etc., all the way up until 11 p.m., and that's all the hours of the day. So it's actually much easier to do this without an arithmetic series, because without an arithmetic series, we're just going to be adding up all these numbers, right? 12 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11, and then times 2 plus itself again. right? So really, we're just adding up the numbers from 1 to 12. So in the sequence, it starts at 12, but when we do a series is a sum. So if I want to add up the numbers, I'm just going to move this 12 at the end, and then I can see this sequence of 1, 2, 3, 4, 5 up until 12. Well, that's a very simple arithmetic sequence, right? Where I start at 1 and I'm adding 1 each time. So because this is an arithmetic sequence, right? The sum of an arithmetic sequence of numbers from 1 to 12, it's the average of the first and last terms. So 1 plus 12 over 2, right? Times the number of terms, it's 12. So from 12 a.m. to 11 a.m., it's going to strike 78 times. And then from 12 p.m. to 11 p.m., it's going to strike another 78 times. And that's why I multiplied by 2, right? Times 2 for the p.m. times, and it's going to strike 156 times. That good? Cool. All right, see you, Grace. All right, any last questions? If not, I'm going to sign out too. All right, see you, Raymond. Have a great day, guys. Hope you guys are keeping busy or occupied while doing this. All right. Bye, everyone. Thanks for coming. Hopefully, I'll see you guys soon. If not, take care. Stay safe. All right. Time to stop sharing. Stop.